Today we're going to start a new unit on quadratics. Now, the word quadratic might sound a little bit scary, a little intimidating, but actually quadratic just means that your equations are going to contain an exponent. What exponent do you suppose? Well, you might think that with the word quad, that would be perhaps a 4, but it turns out that that's not the case. You see, a quadratic actually means that there'll be an exponent of 2. Now, up until this point, the kinds of equations we've talked about have had an exponent of 1. We call them linear equations. Now, remember, the exponent is the exponent on x, and because it's an exponent of 1, we typically don't even show it. But do you agree that linear does have an exponent of 1? Now, of course, when something's linear, you get a straight line, and there's many other applications of y equals mx plus b. If you take the equation y equals mx plus b and you just kind of slightly change some of the letters, we could potentially call it bx plus c. It still has an exponent of 1. But what if we have an exponent of 2? Well, we find out that that makes a quadratic equation. And it also gives us a new term in the front of the equation. And that new term, as you can see, has an exponent of 2. Now, we still have the other parts of the equation. We still have the bx and the c, but it's the ax squared that has the most power. Pun intended, because the power is now 2. And what that does is that affects the type of graph that you get and many other things that we're going to study for, of course, a number of weeks. So when we have an exponent of 2, we say that it's quadratic. Now, what kind of equations, or can we get a sample equation of a quadratic? Well, sure. Perhaps maybe something like y equals 1/2 x squared. Now notice again that I don't have any extra numbers. That is, I don't have any of the bx plus c, because they don't, not that they don't matter, but they don't affect the shape of the graph as much. So basically we're just going to focus on the ax squared, or the 1/2 x squared. So what kind of graph is that? Well, let's graph it. And to do that, we just need a graphing tool. We call that Desmos. And the nice thing about Desmos is that we can actually type in equations, even equations that are new to us, like something like y equals x squared. Now, my apologies, it was supposed to be y equals 1/2 x squared. So let's get that truly typed in. So 1/2 x squared. All right. And look what we get. Well, we get a new kind of graph, at least new for us this year. It's called a parabola. And a parabola is a beautiful kind of graph. It's got this particular U shape to it. There's other things that you may notice about the parabola. That is that it definitely has symmetry. Of course, we see that this parabola only has positive y values. Now, if you think about the nature of x squared, that is, if you think about the nature of squaring numbers, you're only going to end up with positive values, which is why our graph has this particular, again, shape and direction. What if we looked at y equals negative 1/2 x squared? What if we looked at putting a negative sign in front of this equation? Well, let's go back to Desmos and see what happens. I could type in a new equation, or I could just change my existing one. I'm going to choose to just change it so you can see that I end up with, again, a parabola. This time, though, the parabola is opening down. If you think about it, we basically have made all the numbers from the first parabola, we've made them now negative or opposite. So it looks like when you have an x squared, you get this new shape. And this new shape, a parabola, is something that can be seen all around. As you'll discover, parabolas are everywhere. In fact, I have a little video to show you that will kind of just get you thinking about where parabolas, where they show up. So let's take a look. A parabola in nature, another parabola in nature, and another natural shape. Some parabolas can be man-made, even these aqueducts from early times. Now here we see gravity creating a parabola. And similar again, gravity creating a parabola shape. Remember, quadratic functions are just functions that are U-shaped, and one of the most common ones does involve gravity. The path of things that go up and come back down will always be a parabolic shape. Whether the object is shot, kicked, or in this case, like a slingshot, as things go up and down, gravity will grab a hold of them, create that parabolic motion. We're gonna find out that we can look at graphs and parabolas to find out things like a maximum height, distances that things travel, from where they start, and even how long something is up in the air. So the whole point is that parabolas are all around us. Of course, again, when we say parabola, we mean a quadratic kind of equation. And what we want to do now is we want to dig a little bit deeper into the specifics of a quadratic equation. We're going to end up using our sheet, our introductory sheet with parabolas in standard form. Where I actually want to start is by filling in the fact of what's known as standard form. And the standard form equation for parabola was that ax squared plus bx plus c equation. And again, notice that it's got the x squared, and that's what makes it quadratic, because a quadratic function will always have the x squared, which creates that U-shaped parabolic function. Let's graph a parabola. I'm not going to use any specific numbers in an equation at the moment. We're just going to graph this by plotting some points. Now, if you find the point -3, -2, you can plot that, -3, -2. I'm going to also plot the point -1, 0, and over here at -2, 3, 4, -5, 0. And let's find one more point. How about up here at -6, 4, and over here at 0, 4. And so we basically have plotted some points that when we connect them, we will get the shape of a parabola. And just connect those points. Connect those points as smoothly as you can. Kind of get the feel for drawing that type of graph. Now, the cool thing about the graph that we drew is that we can be sure that the coefficient, that is the a value in the equation, would have to be greater than 0. And that's simply because the parabola is opening upward. Let's make another parabola. Again, we're just going to kind of pick some points. Just follow along the best you can as you grab these points. I'm going to try to plot the point 1, 4. I'm going to plot points at negative 1, 0, and over here at 3, 0. And then negative 2, negative 4, and 4, negative 4. This time when I connect the dots in the shape of a parabola, I am forced to draw my graph opening downward, and that's because the a value, that is the coefficient of this graph, we can be sure would be negative, which can be represented as being less than 0. So as you can see, parabolas can open up, they can open down, and either way, we still have a quadratic equation, again, with that x squared and an a value either being greater than 0 or less than 0. Now, depending on the way that the parabola opens, we find out that the vertex, which is a very important point, will end up making a minimum or a maximum. Let's take a quick look. Most of it's just kind of visual and easy to see that the vertex for this particular graph, that is the point at the bottom, is actually going to be a minimum point. But again, notice that we have the vertex, that point in the middle. Over here, we also have a vertex, but this time that vertex is going to be a maximum, simply because it's the highest point on the graph. So a vertex is a pretty important point. It's kind of that point in the middle, and it can be a minimum or maximum on the graph depending on which way it's opening. Continuing, we can deduce that every parabola is going to have a line of symmetry that passes through the vertex. Sometimes we call this the axis of symmetry, axis or line of symmetry, simply dividing the parabola in half. And for each one of these graphs, again, notice that this axis of symmetry always goes through the vertex. Let's record that again as the axis of symmetry. Again, it's called the axis of symmetry. And one more sort of important concept, at least one more group of points on a parabola, we call them the solutions. Now, the solutions of the quadratic equation are going to be pretty important to find. It turns out that they are the x values that make the function equal 0. And these solutions actually have some special names. We call them roots. Sometimes we call them zeros. And quite simply, sometimes we call them what they end up being, which are x-intercepts. So the solutions, again, the roots, the zeros are the x-intercepts. They end up just being important numbers. And we can label them perhaps with like an R. And notice that for both of the graphs that we have drawn here, that these things called the roots, well, it ends up, looks like that there's 2 of them per each parabola. See if you can label and basically describe the important parts of each of these parabolas. The vertex with a V, the axis of symmetry, you can either draw it or call it the AOS, axis of symmetry. We have the idea of the direction of the parabola, either opening up or opening down, depending on the A value. The roots, some points, and is the vertex a minimum or maximum? I'm just trying to analyze each one of these parabolas. So how'd you do? The vertex might be one of the most important points. It's where we're going to start here. It, of course, for this graph is a maximum. You might even be ready to label or to notice the axis of symmetry. We can put that on here. At x equals 2, we can label it axis of symmetry also. There we go. What else do we need to decide here? This parabola opens down, so the a value is going to be less than 0. Did you come up with the roots? The roots are those special spots that are actually like the x-intercepts. And then there's definitely many ordered pairs along this parabola. I see an ordered pair here at 0, -3. Over here, you might notice that there's a point that is kind of connected with it. It's actually like a symmetry point. Looks like that one's at 4, -3. Again, it's like a symmetry point simply because it's symmetrical with the axis of symmetry. And there's no reason I can't label the vertex as 2, 1 as my third ordered pair. Here we have a different parabola. Again, it looks like that it's got a vertex. All parabolas do. This vertex is a minimum just because it's at the bottom of the graph. We have an axis of symmetry that always goes through the vertex. Notice how it divides the graph equally in half. It's at x equals 1. We can call that the axis of symmetry. Again, AOS. This parabola is opening upwards. Since it's opening upwards, we know that the a value, that is the coefficient's got to be greater than 0. And what else did we need to do? We see some roots here. These roots look like that they might be some decimals. That's not that big of a deal. We can just call them what they are. Maybe it's about 3.5. Maybe it's about -1.5. And then when it comes to just some other ordered pairs, they're all over the place. Here's an ordered pair at 0, 5. And as you might notice, there's always going to be a point that's symmetrical with that. Looks like that one's going to be at 2, -5. Symmetrical just means that the point is exactly on the other side, again, of that axis of symmetry. The vertex could be our third ordered pair if we want to label that as 1, -6. So whenever you have an x squared, an ax squared, we now have a quadratic equation, and quadratic equations are parabolas. So let's look at our first kind of specific quadratic equation that's in standard form. Now remember, standard form is just when you have an ax squared, then you have a bx and a c. And when we have numbers filled in for all of these, we end up with an actual standard form equation, perhaps like this one, where we have -1/2 x squared minus 2x plus 1. Now keep in mind that the number in front of x squared is actually your a value. The number in front of x is your b value, and then the number that kind of stands alone is your c value here. That's specifically what we mean when we discuss or talk about a, b, and c. Now, to graph this equation, it would be helpful if we had the vertex. The vertex ends up being one of the most important points, and we end up with one of the most important formulas. It's the formula for the vertex of a parabola. It's just the opposite of b over 2a. Now, the opposite of b over 2a is referring to the b value that was in our equation. So we're going to be doing the opposite of -2 over 2 times a. Now, a is the -1/2 that was in our equation. Now, when you work out this little fraction, we want to do kind of like the numerator, then we want to do the denominator. That'll give us just a +2 and a -1, which ends up working out to be -2. Remember, though, we're trying to find the vertex. The vertex is an actual ordered pair. An ordered pair means that I have to have an x and a y. So in order to come up with the y value, what I'm going to do is I'm going to plug in this x value. Now, where am I going to plug it in? I'm going to plug it in to my equation. And notice, though, that I'm going to end up plugging it in 2 places. So when I plug in -2 for x, that's going to give me the y value. And so I want to, first of all, recognize that it gets plugged in 2 places. And then I definitely want to carefully compute this, most likely on your calculator. Now, what I would encourage you to do is to use your calculator. You can kind of break it into some steps if you want, or you could just type it in straight from beginning to end. If you do the order of operations, you want to do the exponent first, which is going to come out to be positive 4, and positive 4 times negative 1/2 is negative 2. Next, I would multiply negative 2 times negative 2, which is actually going to give me positive 4, and then finally you can add 1 to that. We end up getting the number 3. So my vertex is at negative 2, 3. And I want to record that as an actual point, which eventually is going to end up on my graph. Let's do a little bit more thinking, though, before we maybe get ready to make a graph. What we can do is we can think about if the parabola is going to open up or down. Now, this parabola is going to open down because my a value, which is, again, that front number, is negative. So, again, since a is negative, my parabola is going to open down. Negative, by the way, can be represented as just being less than 0. Now, at this point, sometimes students will think about getting ready to graph the parabola. Sometimes, however, students will still want to jump into making a table of values before you do anything with the graph. But I just kind of want to show you that if I have the vertex at negative 2, 3, and I know that my parabola is going to open downwards, I actually kind of know quite a bit about this graph already. And again, that's based on just the vertex and the fact that the graph opens down. Now, I don't want to just kind of sketch a graph that's opening down. I want to end up with some more specific points. And a lot of times what we ask you to do is to make a table of values to get those specific points, starting with the y-intercept. Now, the y-intercept is nice because it comes from plugging in 0. When I plug in 0 for x, again, that's always going to give me a y-intercept. Now, keep in mind, I'm going to be plugging that into my original equation, that original equation being negative 1/2 x squared minus 2x plus 1. So just imagine putting a 0 in these two spots. And this is why students like this, because when I square the number 0, I still end up with 0. When I multiply by 2, I still get the number 0. It turns out that I end up with just the c value, kind of the last number in the equation. So if you plug a 0 into the equation, you get 1. I would like a few other numbers to plug in so I can actually draw my specific parabola. And so what we suggest that you plug in some numbers that are larger than the vertex. Well, since I know that the vertex is at negative 2, if I want to go larger than negative 2, perhaps I could plug in maybe something like, maybe I could plug in 1. That's larger than negative 2. And perhaps maybe I could plug in 2. Okay, so my vertex is at negative 2, but what I did was I plugged in some numbers that I plugged in some numbers that were greater than negative 2. Sometimes kids like to put negative. I paused here for a second because I was trying to decide. Sometimes kids like to put the vertex in their table. I mean, we already have the vertex, but let's definitely plug in 1, and let's definitely plug in 2. Now, when we say plug in, we're talking about plugging in to the equation. Again, the equation is negative 1/2 x squared minus 2x plus 1. So we're going to plug in 1. Now, again, when I plug that in, I need to very carefully do the order of operations. The order of operations would say to do the exponent first. That's just going to be squaring the number 1 to still be 1. Then you're going to get negative 1/2. Next, I can multiply negative 2 times 1. That's still negative 2. And then finally, plus 1. When you work all that out, you're going to end up with, well, with negative 1/2. Now, it happens to be a decimal, but it would be another point that's on my graph. what else do we want to plug in? We want to plug in the number 2, right? So let's plug the number 2 into the equation. And again, if I do that, I want to very carefully do the order of operations. I know some of you are just putting this in your calculator, but if you square the number 2, you get 4 times negative 1/2 is negative 2. 2 times negative 2 is just negative 4. And then finally, plus 1, this one's going to come out to be negative 5. And so when you plug in 2, you get negative 5. Now, if we go back to this graph, what we want to realize here is that we now have some specific points that we can start to plot. These specific points are from my table. Now, again, I want to plot 0, 1. That was my y-intercept, right? I want to plot 1. Let's get these plots to work here. I want to plot 1, then negative 1.5. That's down here. I want to plot 2, negative 5. So that'll be about right there. Now it looks like I only have kind of like half of a parabola. Well, that's right, I do only have half a parabola because I'm only on one side of my axis of symmetry. The other half of the parabola would be what we call symmetry points. And these symmetry points, we can simply just move to the opposite side of my axis of symmetry to plot those points. And when you plot those points, your parabola looks and feels a lot more balanced. In fact, you're ready to actually draw the graph. This one point doesn't feel quite so balanced. It's just slightly over, so I'm going to put that where it's supposed to be. There we go. And now I'm ready to, again, draw my parabola. Now, not surprisingly, the parabola is opening down, as we already discussed. The a value was negative. It was less than 0. And so we have a nice graph. Now, keep in mind what we graphed. We actually graphed the equation. Sometimes students don't realize that that's what we're trying to do. We're trying to come up with the graph of this equation. And again, notice that the equation had an x squared. That makes it quadratic. And it's not a surprise that we ended up with, once again, a parabola. Can you do one of these on your own? Okay, well, I'd like you to try. Okay, to do this, you have to end up with some points, but they're not just random points. Okay, in fact, the most important point is the vertex. And remember, that vertex comes from a formula. That formula being the opposite of b over 2a. So that's where you want to start. You want to start with the formula, the opposite of b over 2a. Remember, the b value would be the number in front of x. So the opposite of that number, the opposite of negative 4. The a value is the number in front of x squared. So it's always over 2a. So in this case, it's over 2 times 2. You want to kind of do the numerator. You want to kind of do the denominator. And you end up with your x value. Are you plugging that back in so you can get the y value? It's the only way that you can get a y value, again, by plugging into the equation. So we plug in the number 1. And again, you do the order of operations. Now, again, I want you to try to do this on your own. So if you're just kind of copying and listening, push pause and see if you can do a little bit more. I'm going to keep talking about it, but you pause the video between each step so that you can, again, you can try this. Order of operation, you're going to square the number 1. That's still 1 times 2 is 2, minus 4 minus 6. If you do that math carefully, you end up with negative 8. Now remember, we were coming up with a point, and so if we put these two numbers together, 1, negative 8, that ends up being my vertex. The a value is the number 2. Of course, that's greater than 0, so we end up with a graph, a parabola that's going to open up. When it comes to a table of values, there's some numbers that are always part of the table of values. The y-intercept is one of them. Again, because the y-intercept is what happens when you plug a 0 in for x. Well, you always end up getting the last number when you plug a 0 in for x. So our y-intercept is going to be -6, 0, -6 to be exact. We need a couple more points in our table. Now remember, you want some points that are just greater than your vertex. As I mentioned in the previous problem, you can put the vertex in your table. That'll kind of help you to select some numbers that are greater than 1. Maybe you select like 2. Maybe you select like 3. When you select 2 and 3, you want to actually plug those back into the equation. Again, we're plugging them back into the actual equation here for x. So we can plug in 2, and then we're going to turn around and plug in 3. 2 squared is 4. 4 times 2 is 8. 4 times 2 is 8. And then we end up with -6. Now, if you feel like you've seen that number before, you're right. But never fear, when you plug in 2, you get -6. What happens when you plug in 3? 3 squared is 9. 9 times 2 is 18. -12 minus 6. And we end up with 0. Okay, now we haven't actually seen that number before, not as a y value, but we end up with y equals 0. Okay? Let's plot some of these points. Purposely, I'm going to start by plotting the vertex, even though that's like the second point in my table. I had to count a little bit, but we eventually get down here to 1, -8. As you continue to plot points, you have the y-intercept. The y-intercept was at 0, -6. And I have a 2, -6, right? 2, -6. That's going to be over here. 2, -6, and finally 3, 0. Now, those points may not seem like that they are all balanced and symmetrical, but what you want to keep in mind is that the vertex is definitely in the middle. And so the vertex is definitely a point on the bottom. If I think about that, I can draw some of my parabola so that maybe I can better see that there is still an axis of symmetry. That axis of symmetry is definitely going down the middle. And that can help me to locate a few more points. We call these points of symmetry. How about a point that is symmetrical with the x-intercept here, this point that's over here at 3, 0. That's right, that point would actually have to be right here. That would have to be at -1, 0. Now, the way that I drew my parabola needs to be fixed a little bit so that I can better represent, better draw the line that's going to pass through. There we go, that's going to pass through that x-intercept. This parabola is rather skinny. It's kind of the only way to actually connect the dots, but it's still a quadratic equation. I don't know if I really feel comfortable with any other points of symmetry. I mean, I know there's going to be some kind of point up here and over here, but I don't really have those points already on my graph, so I'm going to stop with the points of symmetry that I have. The truth is, the ones that are circled here, even though some of them I already found, are still going to qualify as points of symmetry. Now, there's no homework tonight, but what we'll do tomorrow is we will practice graphing some more quadratic equations, so you can kind of get comfortable, a little more comfortable with how to plug in your numbers, how to come up with your vertex, and even think a little bit here about these symmetry points.